All right, welcome back, lecture number 8. So we'll be looking into chapter 4 on second laws of thermodynamics, okay? All right, so first, a few terminologies again. So a reversible process versus an irreversible process, okay? So a reversible one is the process that in which the system and environment at the same time can be restored to exactly the same initial states that they were in before the process occurred. Okay, if we go backward along the path of the process. Now, on the other hand, irreversible process, the one that system and environment cannot be restored to their original state at the same time. So sometimes you might be having the system restored to initial state, but then the environment has changed. Okay. So for example, if you have this gas initially divided by this wall, the other side is vacuum, you can make a hole, right? So then the gas molecules will diffuse into the other compartments. So then the gas molecule will distribute evenly into the two compartments. Now, in order to that all the gas molecule now go back to the original states, right? So statistically that can happen, right? But it's very little chance of that happening. So in order for that, you have to do work, right? So in that sense, so this is a irreversible process. So most of the um, um, process happen, or I should say all the process happens in the universe, it's irreversible because you could you can have the system itself return to the initial state, but you will have the surrounding being changed. Okay. So that's what happens in reality. So irreversible, like practically it doesn't exist. Okay. All right. So we'll take a look on the statements of the second law of thermodynamics. So there's a few of them, but fundamentally they are the same. They are just expressed in different ways. So the first one is called the Clausius statement. It says the heat never flows spontaneous from a colder object to a hot object. So it goes from the hot object to the cold object. Okay, so that's why heat transfer happens. All right. The application of so he can go from, let's take a look on here. So he can go from hot object here, high temperature T high to T cold. Okay. Now, if you use that, you can actually convert some of the heat that takes into work. Okay. So then you can you can design an engine that's called heat engine. So it takes heat in and then do the work. So it's called heat engine. So in that sense, the part of the heat takes in becomes work, and then the remaining heat becomes excess heat to the environment, or the cold environment. Okay, so that's basically the engine. So typically, the old engines would be always have like water, and you heat the water becomes steam. So steam carries heat. Part of the heat is being converted into the mechanical energy of work, and then the other remaining will be dumped into the environment. Okay, so when the engine was designed, that was only a few, like about 61 years after the first law of thermodynamics is exclusively explained. So that's pretty soon. Okay, consider typically from theory to practical application takes longer time. For example, quantum mechanics, right? It's been quite some time before it's actually applied, or special relativity. Okay. All right. So a heat engine is defined as a device used to extract heat from the source and then convert it into mechanical work that is used for all sorts of different application. That's the definition. Look at the car engine you have. Okay, so it takes fuel in, and also air mixture will be taken in, and so this mixture will be compressed initially. Okay, due to the motion or the momentum of the engine here, so it compress that. Now ignite by the sparker over there, a spark there, so ignite, so then chemical reaction happens, a lot of heat generated due to the chemical reaction. Okay, so the temperature of the gas will increase, it will expand. The gas will expand, so that's mechanical work. Okay, after the work is done, this guy will return to the initial position. So then excess heat will be then dumped into the environment. So this is a cycle. Okay, so then it goes back to the original state and then takes in fuel and air again, compress it, and then spark it, and repeat, cycle repeats. Okay. So when that happens, if you look at the PV diagram, so a PV diagram you can use to calculate what will be the work done by the gas system, and then to calculate the net work, and then compare to the Q takes in and then Q takes out. Okay, so then can calculate what's the work output would that be. So a couple lectures back, we talked about on the PV diagram is use P times dV, right, to calculate the work done by the gas. And it turns out to be the area underneath the curve on the PV diagram from the initial status to the final status. Okay, so from C to D here, then the work done by a process will be the area underneath this guy here. So this area under the curve of CD. From D to A, it actually will not do work because the volume is constant. The same from B to C will not do work, so the volume is constant. So, and from A to B here, it actually compresses. So the volume actually decreases, right? So this is bigger volume, this is smaller volume. So volume decreases. So then it actually does negative work. Okay, so then work will be under this curve. So as a result for the whole cycle here, so it goes from A to B to C to D and then back to A. So negative work, no work, positive work, zero work again. So the net work output will be the area of this cyclic process. Okay, and you can calculate that for the work done for the engine. All right. So compression, this corresponds to the compression part initially, and then takes in the, or this is the after takes in the fuel and air, compresses, and then ignition happens, chemical reaction happens, a lot of heat generated add to the gas system, the piston then expand, or the engine that contains the gas expand, that's the work to the outside, okay, and then now dump heat to the environment for that part. All right, so for engine, mathematically, it's very easy. So heat takes in, E bursts into two, right? Q of out and W. So we are focusing on what will be the W. So W will be equal to the difference between Q in and Q out. So QH minus QC, QH will be Q from the height object, which is Q in, and QC will be equal to Q out to the cold object, okay? A second version of the thermodynamics second law of thermodynamics says it's impossible in any system for heat transfer from a reservoir to completely converted to work in a cyclical process in which the system returns to its initial state. Okay, so in this case, which means you cannot convert all the Q in fully to work. All right, so that's basically what it says. So for a heat engine, there are three main components, right? There's a hot reservoir that provides the heat. There's an engine that does the work. There's a whole cold reservoir that excess heat is being dumped to. Okay, so this is a schematic illustration of what the engine, the three key components. All right, the efficiency of the engine, you'll do the work that can be done divided by how much heat it takes in, right? So work divided by QH will be the efficiency. We use symbol E. So this is the ratio between the two. Work is in joules, Q is in joules. So no units for efficiency. Work is also the difference between QH and QC. So QH minus QC over QH will be work. Then this can be written as 1 minus QC over QH, okay? So efficiency could be work divided by QH, could be QH minus QC over QH, or could be 1 minus QC over QH. All right. Let's take a look on one example here. Okay, so it says an engine receives 660 joules of heat from a hot reservoir and gives off 420 joules of heat to the cold reservoir. So the work done and efficiency. Okay, so I think this should be a pretty easy exercise for you guys. Work done will be the difference between QH and QC, right? QH is 660 joules, QC is 420 joules, so 240 joules of work done. Efficiency will be equal to work over QH then. 240 joules over 660 joules. Okay, so that gives you 0.364 as your efficiency, or I can say 36.4%. Okay, so however you want, either way they are the same. All right, so a pretty simple one. Now let's return to the lecture PowerPoint slide. So now it's not possible to have, or naturally the heat flows from a hot reservoir to a cold reservoir. So that's naturally how it's done. However, it's possible also to make the heat go from the cold reservoir to a hot reservoir. But in order to do that, you need to do extra work. Okay, so that's the working principle for heat pumps and refrigerators. Okay, so let's take a look at them one by one. So normally for heat engine, so heat takes in from hot reservoir and work done by the engine, right? And then for excess heat come to the QC. For the AC or refrigerator, so this is what it does. It takes heat from the cold reservoir of the food inside the refrigerator, and it dumps the heat to the hot reservoir. In order to do that, you need to add work into that. So typically electrical work needs to be added, okay? So then it becomes hot, the heat extends to the hot reservoir. So using this notations, QH for the heat dumped to the hot reservoir, QC for the heat removed from the cold reservoir, and then work done, electrical work supplied by the refrigerator, we can still write the same equation, QH equal to QC plus W, okay? This is what a refrigerator look like, okay? So it takes heat from the food here, okay? And then heat will be actually dumped into here with this guy. The compressor pump here does the work, okay? So QC plus the W, and then that equal to QH dumped to the environment, okay? So if you have the refrigerator door open, right? So the total heat you can see from here, right? For the room, actually will get more heat, right? Then it can actually extract, right? So in that sense, if you are you want to open the AC, the refrigerator door in order to cool down the room temperature, so that's not possible, right? It will actually end up being heating it up. All right. So for a refrigerator, if you want to buy a refrigerator, what you are looking for? You are looking for high efficiency, right? So that means it can take out as much as heat as possible from by the work that it can supply, right? So this is called the coefficient of performance of for a refrigerator, K sub R, equal to actually QC over W. Okay, so QC, the heat can remove over W, and that's equal to QC over QH minus QC, okay? Because W is difference between QH and QC. So example on this. A refrigerator with a coefficient of performance 1.75 absorbs 3.45 times 10 to the 4th power joules of heat from the low temperature reservoir during each cycle. How much mechanical energy is required to operate the refrigerator for a cycle? How much heat does the refrigerator discard to the high temperature reservoir during each cycle? And see if the refrigerator has a power of 150 watts, how long does it take to cool 500 grams of water from 20 degrees Celsius to 2.00 degrees Celsius, okay? So let's take a look on this one. So it says its coefficients of performance 1.75. So that's COP equal to 1.75, and we know COP is defined as Q of C it can take divided by the work needed. Okay. So QC, it says it removes that much or absorbs that much, so that's QC. It's asking you for how much mechanical work. All right, so I think we have 1.75 equal to QC, which is that over work. So we can calculate work pretty easy. So 1.75 equal to 3.45 10 to the fourth power over the work needed. So that gives you work equal to 3.45 10 to the fourth over 1.75. And it turns out to be 1.971 times 10 to the fourth joules. Okay, so that's how much work needed for each cycle. B, how much heat does the refrigerator discard to the environment? So that's looking for QH. QH should be QC plus W. Okay, so the two add up, 3.45 10 to the fourth plus 1.97 10 to the fourth. So 5.42 10 to the fourth joule. All right, now the last part. How long does it take to cool 500 grams of water from 20.0 degrees to 2.00 degrees? All right, so on this one, we can calculate how much heat it takes off during the process, right? So Q C for the cold reservoir. So it's M C delta T, right? It's for water, so you can look it up for the water. So it says 500 grams, so 0.5 kilogram. Okay, 0.5 kilogram. For this guy, you look it up 4186, or you might have remembered by now. Remember by now, delta T will be 2, right? 2 minus 20. Okay. Now, because we define as the how much heat being taken out, so we probably want to say absolute value of this. So just take absolute value of this guy. Okay. So that's equal to how much heat being withdrawn. Okay. So this gives you 37,674 joules of heat. All right. Now the refrigerator has a power, so power is equal to work it can be done divided by T, right? So we can use this QC that we get. We can calculate for how much work is done, right? And then divided by power will be equal to T. So I think you're looking for T equal to work divided by power. Okay, so look for work first. Work equal or work divided by QC equal to COP. So work over 37,674 equal to COP, which is 1.75. Okay, so your work is equal to 1.75 times 37674 joules. No, actually, no, the other way around. So this is, let's just scratch it out. So QC over work is equal to COP. So then work equal to QC over COP. Okay. 37674 joules over 1.75. So 28 joules of work is needed. All right, so then T being work over P over power, 21,528 joules over 150 watts. So that gives you 143.52 seconds, okay? A little bit over 2 minutes, okay? So that's how much time it's needed for that guy. All right, so back to the slides. Now let's take a look on AC. So AC is similar to a refrigerator, but you can think about the whole house as a refrigerator, as an AC. So AC is typically, there's basically that, okay? So it takes heat from the inside cold air, and then with the work done by the AC, and dumped it to the outside air. Okay, so that's how AC works. Okay. All right. And in the winter time, a heat pump works the same way as an AC or refrigerator. So it takes heat. Actually, now in this time, your inside the house, the air inside the house is the hot reservoir. The air outside is cold reservoir. So it takes heat from outside and with the work done, added together, dumped to the inside air. Okay, so that's how it works. So again, QH equal to QC plus QW. So that's the heat pump. It's the reverse way of AC. So it's the same working principle as the AC, but with the outside being the hot reservoir this time, the inside being the cold reservoir. So on this case, then the coefficient of performance for the heat pump. So coefficient performance of the AC should be the same as the refrigerator then. Okay, so we are not repeating that. So it should be this guy. For now, the heat pump will be the other way around because you want to know how much heat it actually can supply to the house, inside house, right? With the amount of work that can be done. So QP in this case is equal to Q of H now divided by W, or QH divided by QC minus QA, QH minus QC. Okay, so this is the heat pump then. All right. A couple two more statements about second law of thermodynamics. So Kelvin's statement says no system can absorb heat from a single reservoir and convert it entirely into work without additional net changes in the system or the surrounding. So it basically says if you want to just have heat goes from one single reservoir, okay, and you cannot invite entirely convert into 100% work without doing extra work, okay. So basically means you cannot convert heat by 100% to the work, okay. Clausius' statement, a process whose only net result is to absorb heat from a cold reservoir and release the same amount of heat to the hot reservoir is impossible, okay? So going from cold reservoir to hot reservoir, you need to add some work, okay? Just like an AC, refrigerator, or heat pump you have seen earlier. All right, so those are the statements of the second law of thermodynamics. You can also different versions of second law. So this guy, so TH, okay, so totally convert into the work that's not possible. That's called a perfect heat engine, right? So you need to have excess heat dumped, okay, to the environment. From the cold reservoir to the hot reservoir, okay, you cannot do that directly without doing anything else. So this is then a perfect refrigerator, okay? So one statement is the perfect heat engine, the other statement is perfect refrigerator, okay? So both are not possible. All right, now let's take a look on a ideal case, okay? So if you are doing each process so slowly, right? So then you might be able to keep the minimal change to the environment. Let's put it in that way, okay? Or we can actually treat it as no change has been made it to the environment. So this is called a Carnot cycle. So each cycle happens so slowly, so each one of them is quasi-static process, okay? So the total work here, if you start from a particular point, maybe from O, P, Mn, or Mn, OP, whichever it is, the total work done then will be the work enclosed by the cyclic path, okay? Heat in and heat out, you can also calculate from the PV curve, okay? So at the end, you'll be able to calculate what will be then the efficiency of this engine, okay? So for ideal gas, with T being constant, we can calculate, right? So we know how to do that. So integration of PdV, which is nRT ln of V2 over V1, okay? So, and then for adiabatic process, we also seen that earlier last time. So for adiabatic process, PV gamma equal to constant, where gamma equal to Cp over Cv. And the heat, the work done, you can calculate it, okay, for adiabatic process. Adiabatic process can also be written as different forms. So if you use T and V, you can have TV gamma minus 1 equal to constant. Okay. Now, mathematically, you can prove that QH, which is W1 for this some isothermal process. Okay, so you can calculate it. So nRTH line of V M minus over M for adiabatic process. Okay, so you write this equation there. And isothermal compression, now this is the work done, okay, equal to Q because isothermal. Internal energy doesn't change. So the same here is because the T equal to 0, delta T equal to 0, delta E equal to 0. So QH equal to W1. Okay, so both cases you can calculate it. NRTC line VO over VP. All right, and then adiabatic process again for this one and this one. Okay, so typically we consider those two as adiabatic process because that happens quickly. So TV gamma minus 1, okay, TV gamma minus 1 in that sense. So you can prove this. So QC over QH is going to be equal to TC line of VO over VP and then divided by TH. So this gets QC, right? QC over QH. Basically, you can prove that VO over VP equal to Vn over M by using the adiabatic expressions, all right? So then this and this will cancel. They are the same. Okay, so cancel. So QC over QH then equal to TC over TH. All right. So if that's the case, then this is the ideal engine, which is called Carnot engine. Okay, so then the efficiency equal to 1 minus QAC over QH is equal to 1 minus TC over TH. So basically, for a Carnot engine, an ideal engine, the efficiency is going to just be determined by the temperature of the two reservoirs. Okay, now remember when you calculate this, TC and TH should be in SI units of Kelvin. Okay, a lot of times they are going to be given in Celsius. You want to convert them into Kelvins for the calculation. Let's take a look on the example here. Okay, so it says a Carnot engine takes 2000 joules of heat from a reservoir at 500 Kelvin. That's some work and discards some heat to the reservoir at 350 Kelvin. What's the efficiency? How much work and how much heat is being discarded? Okay, so let's take a look on here. The knowns we are given, so it takes in heat. So that means the heat takes in would be the QH. Okay, so QH equal to 2000 joules. It tells you TH 500 Kelvin, TC 350 Kelvin. Okay, so then efficiency, because this is a Carnot engine, you can calculate efficiency using the temperatures given. 1 minus TC over TH. So 1 minus 350 Kelvin over 500 Kelvin, which gives you 0.3 or 30%. Okay, of efficiency on this one. Now B, how much work is done? So work done, you can start from efficiency definition is work over QH, right? So then work is equal to E of Q times QH, 0.3 times 2000 joules, which is 600 joules. All right. And lastly, how much heat is being discarded to the environment. So that's looking for QC. QC will be QH minus W. All right, because W is QH minus QC. Okay. So that equals 2000 joules minus 600 joules. So 1400 joules of heat is being discarded to the environment. Okay. Now back to the slide. The same for the AC refrigerator and heat pump. Okay, so for ACR refrigerator, if this is an ideal engine, we call Carnot refrigerator. Okay, so then coefficient of performance for refrigerator K sub R is equal to how much heat it can absorb from the cold reservoir divided by the work. Okay, work is equal to QH minus QC. So then, because QC and QH are proportional to the temperatures, right? So this will be then, in terms of temperature, will be TC over TH minus TC. Okay. For the heat pump, we are doing QH over work, which is QH minus QC. So then this is TH over TH minus TC. Okay. All right. So to summarize for Carnot engines, okay. So Carnot summarized his study of Carnot engine and Carnot cycle into what's known as Carnot principle, which says no engine works between two reservoirs at constant temperature can have a greater efficiency than a reversible engine. Okay. All right. So that means the Carnot efficiency is the greatest. Okay, so you could have two given temperatures, right? So once you have the two temperatures of the reservoirs, then that's the upper limit you can hit. Okay, you cannot go beyond that. So basically, all right. So we're going to stop here for today, and then we'll be coming back the next for the next lecture. Okay, see you guys.